Okay, I think we'll get started. If you're coming from the GNL project, I encourage you to look at the introductory video for this playlist. Otherwise, we'll be starting today talking about impulses, and this is where we can start to talk about collisions. So a collision is a very short interaction between two objects. So maybe two molecules collide, maybe a baseball bat hits a baseball. We have collisions going on all the time, and it's nice to be able to handle those and answer some questions about those. So lying at the heart of this is something called an impulse, and we're going to be able to see here that impulse can be thought of as in two different ways, and that brings together some important concepts of force and this idea of momentum, which we haven't seen yet, but today is where we'll define momentum. Okay, so what we're looking at here is that if we have let's just imagine a wall and then a free-flowing particle, and it strikes the wall. There's a brief time of interaction where the ball and the wall compress a little. Only in a perfect ideal situation would there be no compression. So there'd be some level of compression, and that would take an amount of time, and then this would bounce back off the wall. So during that time, there's forces acting between the wall and the ball, and we can plot those forces, or in particular the force, if we're thinking about this, the normal force of the wall on this ball. So in general, this will have some kind of curve, and it will take place over time. Usually that time is fairly short. We define an impulse as the cumulative force over that time. So we're looking at the area under the curve here. If you've had some calculus, that's an integral of this curve. And that's the J. Now, we're not going to be able to do, this course is non-calc based, so we're not going to be able to evaluate the integrals of these. Instead, we're going to approximate these by rectangles of this same area. So we imagine this area being a rectangle, so then we'll draw something like this to represent this area. So the length times the width of this rectangle is the area under the curve. Then we define this as the average force, and then this distance as the interaction time, the delta t there. And that defines what an impulse is from a force and time perspective. Okay, well, if we've got a force, then by Newton's second law, here's the second law here, we can get the acceleration by dividing by the mass. So if this ball colliding with this wall be the mass of the ball, then we can also think of acceleration via our kinematic equations as being the change in the velocity with time, right? So if this ball, let's take just what we call an elastic collision, where this comes in at the same speed and goes out at the other speed. So if the speed is 10 meters per second, and then here the speed would be 10 meters per second, but the change in velocity was actually, even though the speed's the same, the velocity has changed because here we're going this way, say plus 20 and minus 20 meters per second. Okay, so that's our acceleration. Now, let's put these two together. So I'm going to take this is equal to this, right, from here, and then I'm going to bring this down, and I'm going to expose the delta here. So that's final minus initial over time. Now, let's bring the mass over to this side and the time over to this side. So we're going to bring this up over here, and we're going to bring that over there. We get, now, impulse right? This is our impulse, and then we get this relation. And so we're going to say this is J, but this is also, I'm going to distribute this M through, right, because the mass is the same. And I'm going to now define this quantity M times V. And that's the definition of this property called momentum. And we talked about, very first lecture, we talked about momentum as being one of the conserved quantities, and we'll talk about conservation of momentum coming up here in the next few lectures. So momentum is a very core property, and we see it here for the first time. And notice here, this is the final momentum, this is the initial momentum. So J is also equal to delta P. And these two relations then are powerful because we can put them together and get the force time version of impulse and the momentum version of impulse put together to solve some problems. All right, let's take this case of a ball striking the wall. So there's a certain mass and a velocity that's going to give rise to an initial momentum vector, right, and a final momentum vector after the collision. If we first draw PF, so I'm going to pick this up, put this at this point, then we're going to add head to tail negative PI, so that's going to take this off in this direction, and then the resultant vector is the impulse vector. So what we're seeing is the wall is providing an impulse in this direction. Very easy to see if you're thinking about a baseball or a golf club striking a golf ball or a baseball bat striking a baseball, that the force is in this direction. The wall is sitting still, but its normal force is still applying the impulse in that direction to change the direction of the object. All right, let's take an example. Let's imagine stopping an object. So let's imagine a crash test in an automotive testing. And we're going to take this test car and certain mass, certain speed, and we'll crash it into a wall. We'll say that it takes, because of the way the car is designed to crumple, it takes 3/4 of a second to crumple. So what's going to happen when it crumples? We'll be sitting there at 0 meters per second. So we've gone from 20 meters per second to 0 meters per second. Well, we also know this is carrying this mass, so let's write J in this way. We have J equals delta P is final, so mass times 0, and then minus initial, which is mass times the initial. So that gives us our minus 22,000 kilogram meters per second. Now let's take, and that's J, let's set it equal to this. So that means that this J is equal to F average times the delta T. So we can solve for F average and we get 29,000 newtons. So that's the normal force applied by the wall during the collision. It's negative because it's applying the force that way. Let's look at the acceleration then. So the acceleration is the average force divided by mass. So here we get minus 26.6 meters per second squared. We can sometimes we want to put this in the context of the gravitational acceleration. So if we divide by 9.8, we get 2.72. So the driver would experience minus 2.72 g of force there, or of acceleration. Sorry, of acceleration. Okay, let's do this elastic rebound case. So in an elastic rebound, the velocity in equals negative of the velocity out, or the velocity out equals negative of the velocity in. So they're equal but opposite, expressed here. Let's write our J with this version. So J is that, and we now can write out what the momentum is. And now we can get two versions of J. We can get where we replace the in via this equation, and we get that J is 2 times the outward momentum. Or we can replace with the in, and we can see that J is minus 2 times the inward momentum. So for example, if we had a 20 kilogram mass striking a wall in an elastic rebound with 5 meters at minus 5 meters per second, then the initial momentum would be 1 times minus 5 is minus 5 kilogram meter per second. So J is going to be 2 times that. It's going to be minus, right? Minus 2 times that, and that will give us a positive 10 kilogram meters per second. Okay, so we're going to do some in-class worksheets and to get a lot more practice with this. And in fact, throughout the dealings with momentum, we're going to be spending more time in the class with worksheets. And so this is a period for those of you coming from the GNL project where there'll be less video support for that. So you'll be a little bit more on your own during that section.